Hello everyone. During the next several minutes, I want to just provide a few examples to kind of model how we can think about some of these counting problems without really giving you any notes, because we hopefully talked about that in class, or you can read in the text. Many times with these counting problems, it's the plan of attack that's so important. Of course, we're going to be using some very important things. We will be using factorial notation. Many times we can write our answer in factorial notation and leave it at that. Unless it's a relatively small number. We will be using the counting principle, sometimes on its own, other times in conjunction with some of these other methods. We may be using permutations, but as I said in class, permutations can usually be thought of as really just a different application of the counting principle. And of course, we'll be using combinations when we're trying to collect a group where order does not matter. So let's get into these examples. Talk through them. I'll try to provide a little insight about why I'm thinking the way I'm thinking, and then hopefully it will help you as you work through some of the problems in the problem set. The first situation is we have a question as to how many three-digit numbers with no digits the same can be made using the numbers 0, 1, 3, 5, and 8. Now, the first part is there are no restrictions. Now, of course, there are 5 digits here. But if I want to make a 3-digit number, that first digit cannot be a 0, because then it's just a 2-digit number. So the counting principle is really going to help us out here. I like to put the blanks there because it tells me I need to put some number or a combination in each one of those blanks. Then ultimately I'll multiply the numbers represented by each blank. But I know that I can 1, 2, 3, 4 put 4 different numbers in that first space. Now once I choose one of these 4, there are still 4 numbers I can choose, because now I'm allowed to use the 0. But once I've chosen 2, there's only 3 left. So it's really not a permutation, it's just a simple counting principle problem. And then of course 4 times 4 times 3, I hope is 48. So 48 different 3-digit numbers. Now, what if we want the number to be less than 500? Again, it's a 3-digit number. If it's less than 500, we're not going to be able to use the 5 and the 8 in the first spot. But we also can't use the 0, because then it wouldn't be a 3-digit number. So there's only 2 numbers I could use. Of course, it'd be a 1 or a 3. Now, once I've done that, I don't know why I said that, less than 500. Okay? That's right. Once I've chosen one of these, then there are 4 numbers that I could use. And it would still be less than 500. And then once I've chosen 2, there are going to be 3. And there would be 24 different numbers less than 500. Now remember, all these counting techniques really take the place of actually counting. Which means if I listed all the possibilities, and there'd be a lot of them, this is how many would have numbers we could get total. This is how many would be less than 500. The next must be greater than 300 and even. Now, because there are 2 conditions here, we're going to use cases. Because it's even, one case could be that the last digit is a 0. So there's only one way to do that. The other case could be that the last digit is an 8. There's only one way to do that. And then whenever we separate things into cases, we're going to add those numbers. So in this first one, if it must be greater than 300, I can only use these 3 different numbers to start, but I'm not using that 0, so it would be 3, because I'm using the 0 at the end. Okay, once I've done that, I've got the 0 gone. I've got these others gone. There are 3 different numbers to use. So that part gives me 9. And then for the next part, I've got the 8 at the end. So I'm using that 8. We want it to be greater than 300. There are only 2 numbers left that would do that for me. Then once I use one of those 2, there are 3 left. So we end up with 15. Now you could check it because coming up with 48 different possibilities and seeing that these are the two, you could get that by counting. On to the next, more of a geometry-based one. We want to find out how many diagonals does a convex 20-sided polygon have. Well, of course, you could draw a 20-sided polygon and connect them all the vertices, and find out how many diagonals there would be. That wouldn't be impossible. It just might take a while, and you'd have to worry about counting them. So we want to come up with a mechanism to do that. Well, here I have to ask myself, what makes a diagonal? Well, a diagonal, of course, connects two vertices that aren't adjacent. But that seems too complicated. So I am just going to find out how many ways I can just connect two vertices, regardless if they're adjacent. So I may start with the fact that it is a combination. I don't care which two vertices I pick in which order. So there are 20 vertices, and I'm just choosing two of them. There's only one trouble with that. I've also counted the sides. So I subtract 20, I do that calculation, and I get my answer. So it's a 190 minus, that'd be 190, it'd be 10 times 19. Yep, so it'd be about 170. So I really don't want to count that many. Now, some people may realize that this is just starting with one vertex. You can go to 18 different vertices to get a diagonal. And then the next one, you can go to 18. But then after that, it's going to start scaling down one. So you could somehow create a system to count these without having to count them all. But there should be 170. So a little bit of insight here that we just wanted to pick two from the 20. Similar to the one I gave some of the classes as examples, where we had those two lines with a certain number of dots on the lines or points, and we had to connect all of the points of one line to all the points of the other, and we wanted to figure out how many intersection points there would be as a maximum. So it starts off in geometry, but it can become a counting problem. Lastly, we have a committee of 4 is going to be chosen from 7 men and 6 women. How many committees can be formed if there are no restrictions? Well, if there's no restrictions, it's simply going to be a combination. The combination is there are 13. I'm choosing 4. Whatever that number turns out to be, that's the total number of committees I can come up with. Now for the other part, we realize that we want 2 of each sex, 2 men, 2 women. So in that case, it's almost like a counting principle. But within each part of the counting principle, it's a combination. It's basically asking, how many ways can I choose 2 of the 7 men? How many ways can I choose 2 of the 6 women? And then I'm going to multiply those together. This is the number of ways I can choose 2 men. This is the number of ways I can choose 2 women. So the number of ways I can choose both of them would be that. Okay, and it does add to 4. Now the next one, at least 1 of each. Well, this is where you have to kind of think about how you want to handle that phrase, at least. At least could be 1 man, 3 women, 2 men, 2 women, 3 men, 1 woman. So we would have kind of this situation 3 different times, and as we did back here, we would have to add those quantities together. But another option is kind of coming through the back door, thinking that, I'm going to think of a full group and then subtract. So instead of at least 1 of each sex, I would basically come up with the fact that we have the whole total and we want to subtract if we have either no men or no women. Now, I don't think it's really that much better, but I'm going to go about it that way just to demonstrate that method. So the total number, of course, is going to be that combination of 20, choose 2. Then I'm going to take away that if there are no men. If there are no men on the committee, then that means I'm only choosing 2 of the 6 women. And then I'm going to subtract, there's no women. And in that case, I'm choosing all men. And that would be one way to calculate the number where there's at least one of each. It's just going to be all of them when you take away the committees that are either all men or all women. So I said the other option would have been to look at it more of a direct approach, but you'd have to deal with different cases. So that may not be enough to be comfortable with all of the counting procedures, but in the problem set from section 1.4H, the latter part of it is about these types of problems. The early part is more of a procedural comfort with simplifying factorial notation and complicated expressions that have the factorial notation. So hopefully this helps out. In class, the next time we see each other, we'll be talking a little bit more about the binomial theorem. So in the meantime, make progress on section 1.4H. Also make progress on the proof handout involving the principle of mathematical induction. And then even further back, any of the other proofs that you might still be working on. Let me know if you have any questions, and have a good day.